Okay, we're talking about logarithms now, and we're going to start off with what's a logarithm? Why do we even need logarithms? And to illustrate, for example, we talked about in Moore's law how the number of transistors that you could fit on a chip has been doubling pretty much every 18 months since 1971. But you can see on that scale on the left-hand side that if we went with a linear scale, the graph would shoot upwards so fast that we wouldn't really be able to see what's going on. And in fact, we did that in class, and you'd have to walk, thousands of yards just to be able to plot the next point after a while. So there is a need for a different type of measure besides just linear. So what is a logarithm? Well, a logarithm is just an exponent. Okay? What's a logarithm? A logarithm is an exponent. What's a logarithm? It's an exponent. If you ever get stuck, just remember, what's a logarithm? It's an exponent. All right, so to illustrate that, one of the other things besides, Moore's law and labeling the side of that graph there is the Richter scale measured for earthquakes. And if we've got, the Richter scale all the way down up to 9, you might think, okay, each one of these represents, perhaps if it was a linear increase, perhaps 2 would be 2 times as powerful. Earthquake of 2 would be twice as powerful as 1. Earthquake measure of 6 would be twice as powerful as 3, maybe 3 times as powerful as 2, but that's not the case. Each one of these, this is actually a logarithmic scale. This is a logarithmic scale, so each one of these numbers represents an exponent. These all represent exponents. This is logarithmic. It's a logarithmic scale, which means these are all exponents. Okay, and logarithmic scale. These are all exponents. Our book is slightly simplified in the way we describe this, but basically, letter 0 on the Richter scale, we have just this energy constant E. 1 would be just E times 30. 2 would be E times 30 squared. E times 30 to the third, get to 30 to the fourth. This E just represents a constant that we're not going to get into. Again, this is simplified. But as you go up, you can kind of see the idea that these numbers do not represent just linear increases. Okay? Each one represents the exponent. The exponent. So each increase is going to represent approximately a 30% increase of the one before it. So if we do just a quick practice example, how much more powerful was the 1906 San Francisco earthquake, 8.0 on the Richter scale, compared to the 1989 Bay Area earthquake, which is a 6.9? And what we can do is just simply set up a ratio, this one over this one. So the 8.0 on the Richter scale would be this, E times 30 to the 8. Remember, 8 is the exponent. Over, compared to this guy, which is 6.9. Right, so that'd be E times 30 to 6.9, almost at 7 there. 9, we compare these guys. E over E, whatever that was, it just crosses out, becomes 1. When you have an exponent over an exponent like this, remember you can subtract them, so we get 30 to the 8 minus 6.9, so we get 30 to the 1.1. 30 to the 1.1, so 30 to the 1.1. Approximately 42 times more powerful. Which is kind of crazy if you think about it. I mean, the numbers are so close, and yet this 8 was about 42 times more powerful than this 6.9 earthquake. So now let's check out the definition of a logarithm. Remember, a logarithm is an exponent. A logarithm is just an exponent. So if y equals b to the x, so we have an exponential function here, just like we've been talking about, then log, starts with logarithm, base b. So the b is the base of the exponential function, it's the base of the logarithm. Write it underneath, subscript, log base b of y. Getting a little blurry here, come on now. Log base b of y equals x. And if we just stop and think about this for a second, it makes sense because remember, what is a logarithm? It's an exponent, right? What's a logarithm? It's an exponent. So here's the logarithm part. There's your exponent. Right here, there's the exponent. Okay, so what this is really saying, what you should always ask yourself when you're trying to evaluate, is you're saying b to what exponent gives y? Right? B to what exponent gives y? Because that's what you're trying to find. A log is just an exponent. So what can we do with these guys? Let's go ahead and first off and just start practicing a little bit, writing in logarithmic form, using this definition here. So number one, let's write in logarithmic form. Okay, so starting off, so let's just do some facts here. 729 equals 3 to the 6th. And part B, I don't know, 1/2 cubed equals 1/8. And we should leave it there for now. So let's see, first off here, I've got the base here is this 3. The exponent part is the 6. So I'm going to rewrite this as log, the base is 3, log base 3 of 729 equals 6. Right. For this one, my exponent is the 3, the base is the 1/2, so I'm going to get log base, this base still comes underneath, write it in subscript, 1/2 of 1/8 equals 3. Okay, so again, just remember, what's a log? It's an exponent. What's a log? It's an exponent. The exponent always goes on the other side. Let's try a couple more examples. Let's do a simpler one just so we can kind of see what's going on. 2 cubed equals 8. And then finally, we'll do 10 to the 0 equals 1. All right, let's write this in log form. So again, we got our base here. This one's our base. This one's our base. Here's our exponent. So we just write log base 2 of 8 equals 3. Log base 2 of 8 equals 3. Over here, we're going to say log base 10 of 1 equals 0. Okay? And again, when you're evaluating this, the way you pronounce this log base 2 of 8. This is log base 2 of 8. All right, so we know how to convert to log form.